In this video, we're going to be talking about the history of the periodic table, the electron configuration, and also how each elements are classified within the periodic table. First, let's look at the history. So the first type of periodic table was invented by a Russian chemist named Mendeleev. And basically, this guy, he organized it based on the atomic weights. However, another chemist, an English chemist named Henry Moseley, categorized it by using the atomic number. So the way he was able to categorize it by using atomic number was using the electron configuration, which we will get in a second over here. The atomic number practically is the exact same as the amount of protons and electrons there are. And the reason why is because protons are positively charged particles and electrons are negatively charged particles. And since an atom is generally neutral, the amount of protons there are also has to equal the amount of electrons there are, so the atom can stay neutral in general. And neutrons, they're neutrally charged particles, which basically mean that they do nothing at all. It's categorized through groups and periods. Groups go vertical, which means they go through columns, but periods go horizontal, which means they go in through rows. Periods determine how many of these outer rings there are in the atom, and the group just help classify where it is. Let's look at lithium over here. It's in group 2. So that means that when looking at the anatomy of an atom, there is, of course, the nucleus. Then after that, there's the first outer ring and then the second outer ring. And the reason why there's 2 outer rings is because it's located in period 2. Let's say it was located in period 6. That means that there must be 6 outer rings. So the atomic number is 3, there must be 3 protons. However, what do we do with the electrons? There's 2 outer rings, but 3 electrons. How do we know like 1 electron should go here, or 2 electrons should go here, or 3 should go here, and none should go here? How do we know how to classify that? Well, basically, here's how it is organized. So the first ring should have 2 electrons, the second ring should have A, the third ring should have A, fourth ring should have 18, fifth ring should have 18, sixth ring should have 32, and seventh ring should have 32. And since there's only 7 periods, that is the end, okay? So since the first ring must have 2, we'll put 1 here, then 1 here. And instead of putting 8, since there's 3, that means that the amount that is left over would be the amount of valence electrons there's going to be. So since we already have 2, and 3 minus 2 is 1, 1 is the leftover amount of electrons, and that is the valence electron. So 1 is the valence electron. So we put it and categorize it as 2, 1. What I mean by 2, A, 18, and so on to 32, basically I'm just saying like these rings, the max they could hold. So the first ring can maxly only hold 2, second ring can only hold max A, and like the fourth ring can only hold max 18, sixth ring can only hold like max 32. And that is the max they can hold in general. Valence electrons are basically the leftover ones on the last ring. So let's look at another one. So what's the next element? Sodium, which is Na. It has 11. So let's do sodium. We'll keep in mind of this, okay? It has, since it is on period 3, it must have 3 rings. So protons are 11. So 1 ring, 2 ring, and 3 ring, okay? Now if you're wondering what this like circle here is over here, that is the nucleus. The nucleus is the one that contains the protons, the neutrons. So since there's 11, that must mean that 2 is the max that can hold in the first ring. So we'll put 1, 2. 8 is the one that can hold in the second ring, max. So 1, 2, 3, 4, 5, 6, 7, 8. So those are 8. Now, what about the leftover? So 2 plus 8 is 10, meaning that 1 is left over. See how convenient it is? 1. We'll just put 1 there, and the configuration is 2, 8, 1. Let's look at it on one last one. So after sodium would go potassium, which has 19. And since it's on period 4, it has 4 rings. So P equals 19. This is going to be the nucleus. First ring, second ring, third ring, and then fourth ring. So max it can hold for the first ring is 2. Max it can hold for the second ring is 8. Max it can hold for the third ring is also 8. okay? I didn't exactly evenly distribute it because I'm in a bit of a rush. And 2 plus 8 is 10, plus 8 is 18, but since it has 19, that must mean that 1 is left over. Look, now let's look at it. 2, comma, 8, comma, 8, comma, 1. So let's look at the overview. There's one valence electron, one valence electron, one valence electron. Do you see this? That shows that in this group, there's always going to be one valence electron. And this is why mostly through his genius was able to place it all together based on the configuration. Since they all had one valence electron, that must have meant that they had practically the same chemical properties. However, let's look at the color. One little difference. Hydrogen. It has a different color that matches over here. Hydrogen is known as a noble gas, and hydrogen shares qualities or characteristics of both in group 1 and group 18. So he had to strategically put it in both places while color coding it so that you would be able to understand, or people would be able to understand in the future, how the periodic table worked. So let's just look at two more over here in the second group, and then we can come to a conclusion. So let's take a random one, calcium, okay? So calcium over here, Ca, and there's 20, okay? So that must mean that protons equals 20, and calcium is located in group, so it's on period 4, meaning it must have 4 amount of outer shells. So this is the nucleus, this is the first shell, second shell, third shell, fourth shell, okay? So we're going to be using the exact same way we did it, okay? So the first shell will of course have 2, so 1, 2, since that's the max it can hold. Second shell could hold max 8, 1, 2, 3, 4, 5, 6, 7, 8. Third can hold also max 8, 1, 2, 3, 4, 5, 6, 7, 8. And now let's look at it. 2 plus 8 plus 8 is 18, but there's 2 left over this time, not 1, 2 left over. Meaning there's going to be 1 here, 1 here. So basically the electron configuration is 2, 8, 8, 2. So it has 2 valence electrons. So now let's look at another one, something like magnesium, okay? It's on period, I believe 3, and it has the atomic number of 12. So protons is 12 over here. So this is nucleus, and we're going to be doing magnesium. So that means since it's on period 3, 1 ring, 2 ring, 3 ring, okay? And since it's on 3 ring, that must mean that it must have 2 electrons on 1 here. So 2, then 1, 2, 3, 4, 5, 6, 7, 8. So now 8. And since it has 12, and since there are 2 plus 8, which is 10, that must mean that there's 2 left over. So that would be the 2 valence electrons. So 2, 8, 2 is the configuration. And look, we have 2. So basically, the conclusion is, according to the amount of periods there are, so whatever period you're on, the number of period that you're on would represent the amount of shells or outer rings the atom has. And based on looking at this sequence over here, we could see that based on the position of the element would represent how many valence electrons there are, and using the atomic number we could see how many protons and electrons there are in total. The amount of valence electrons there are in the element, that would show how it is categorized based on its chemical properties on the periodic table. This is all about the history of the periodic table, how it's categorized, and what a valence electron is, and the configuration of it.